At the dawn of the 20th century, science believed it had almost everything figured out. Newton's laws explained motion, Maxwell's equations explained light, and the universe seemed like a perfectly wound clock. Yet cracks began to appear, small puzzles that refused to fit. One of those puzzles was the mystery of heat and light. In the year 1900, a German physicist named Max Planck tried to explain how objects glow when heated. Classical physics said they should radiate infinite energy, which made no sense. So, almost reluctantly, Planck suggested that energy might not flow smoothly, but instead come in tiny, separate packets, which he called quanta. He had no idea that this quiet proposal would launch an entirely new era of science. That moment, in a sense, was the birth of quantum physics. Just 5 years later, in 1905, a young patent clerk in Switzerland picked up Planck's strange idea and took it further. Albert Einstein proposed that light itself was made of individual packets of energy, particles we now call photons. His bold explanation of the photoelectric effect showed that light, the very symbol of a continuous wave, could behave as a stream of particles. The boundary between waves and matter was beginning to blur, and Einstein's insight would earn him the Nobel Prize years later. By 1913, the mystery had moved inside the atom. Niels Bohr, working in Copenhagen, realized that the structure of atoms could not be explained by classical orbits. He imagined electrons circling the nucleus only in specific allowed paths, each corresponding to a distinct amount of energy. When an electron jumped between those paths, light of a precise color was emitted or absorbed. It was a strange idea, but it matched experiments perfectly. Bohr's atom became a symbol of the new quantized world. Then, in the early 1920s, an extraordinary young scientist from France, Louis de Broglie, asked a daring question. If light can act like a particle, could matter act like a wave? He suggested that every moving particle, even an electron, has an associated wavelength. Soon after, experiments proved him right. The once solid world of matter had become fluid and wave-like. In 1925, a 23-year-old German physicist named Werner Heisenberg took an even bolder step. Frustrated with trying to picture electrons as tiny planets, he abandoned visual models entirely. Instead, he focused on the relationships between measurable quantities, the frequencies of light atoms emit and absorb. From this approach, a new kind of mathematics was born, known as matrix mechanics. It revealed something shocking. There are limits to what can be known. The more precisely we know where a particle is, the less we can know about how fast it's moving. This became famous as the uncertainty principle, the end of perfect predictability. But the story didn't stop there. Across Europe, in Zurich, Erwin Schrödinger was searching for a more intuitive picture. Inspired by de Broglie's wave idea, he imagined that electrons were not little dots, but smooth waves of probability. In 1926, he wrote down an equation that described how those waves change in time. With it, he could explain the shapes of atoms and the patterns of chemical bonds. Quantum mechanics had finally taken form, not as a set of strange guesses, but as a coherent theory. In just over a quarter of a century, physics had been transformed. Planck had opened the door, Einstein had revealed light's dual nature, Bohr had given the atom structure, de Broglie had connected waves and matter, Heisenberg had introduced uncertainty, and Schrödinger had unified it all with the language of waves. By 1926, the classical world was gone forever. In its place stood a new vision of reality, one that was probabilistic, mysterious, and astonishingly precise. Quantum mechanics was born, and though no one yet understood its full implications, it would soon power the technologies, the computers, and even the philosophy of the modern world.